Hello everyone and welcome to Robot Operating System version 2 Jazzy tutorials. In this tutorial we explain how to model a differential drive robot from scratch in ROS2 and Gazebo and how to write a C++ code and package for controlling this simulation. The robot simulation is shown over here. Namely, this is the Gazebo simulation of a mobile robot. This simulation takes into account robot parameters as well as the robot dynamics, including mass, moments of inertia, and other parameters. On the other hand, here is the C++ code that's used to control this robot motion. Here, we have programmed a circular trajectory. Namely, in this code, we set the linear and angular velocities for controlling the simulation. Here is the linear velocity and here is the angular velocity. And finally, we have written a complete code that sends periodically these control actions. To develop this simulation and in order to implement the controller, we have written several files. First of all, we have written this XML file that implements the robot geometry and robot mass and inertia properties. Then we have written an additional XML files that defines the plugin and defines additional Gazebo properties. Then we have written a bridge parameters YML file that defines a bridge between ROS2 and Gazebo simulation. Then we have written this launch file, which is a Python file that tells ROS2 how to run everything, that is, how to run all the nodes, including Gazebo, including Robot State Publisher, including the bridge between ROS2 and Gazebo. And finally, we have written the C++ file, which is the controller for our mobile robot. In addition to this, we have written these two configuration files that define how to build everything. In addition to these code files, we have also created two manual files thoroughly explaining how to implement this simulation. Here is the first manual file that explains all the steps that you need to perform in order to implement this simulation. Here it is. It has around 8 pages, and in addition to this, we have created this manual file explaining the dynamics and geometry of the robot, giving all the formulas, explaining how the coordinate system should be placed, and giving very important information about the volume, about moments of inertia, and other geometrical and dynamics properties of this robot. Links to these files, that is, links to these two manual files and all the codes explained and presented in this video tutorial are given in the description below this video and in the comment section. This video tutorial is self-contained. Namely, in this video tutorial, we thoroughly explain all the steps that you need to perform in order to implement the model. That is, we will explain every single line of code. However, in order to reduce the length of this video tutorial, we might quickly go over certain steps, and especially the steps related to the modeling of the geometry and the dynamics of the robot. If you want to learn more about modeling and about the dynamics of the robot, then my suggestion is to watch this video tutorial. Here is the name. It is on my YouTube channel, and I'm going to provide a link to that video tutorial. However, as mentioned previously, the video that you're currently watching is self-contained. Here is a more detailed summary of what you will learn in this tutorial. In this tutorial, we explain how to install Gazebo Harmonic in ROS2 Jazzy, then we explain how to write a ROS2 package from scratch, then we explain how to model a mobile robot and its dynamics in Gazebo, then we explain how to connect ROS2 and Gazebo topics and how to send information between Gazebo and ROS2 and vice versa, and finally we explain how to write a C++ ROS2 code for controlling the robot motion in Gazebo. Since a lot of viewers of this channel are completely new to ROS2 and robotics, in this video tutorial we will spend a significant amount of time explaining the basics. And we will start from prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Our suggestion is not to use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. To verify that you have the correct Linux Ubuntu version, you need to open a new terminal and execute this command. To open a terminal on Linux Ubuntu, you need to click here and then search for terminal. And over here in the terminal, you need to type this command. This command will output your current Linux Ubuntu version, and if you see 24.04, then you can proceed further and you can continue watching this video tutorial. Next, to implement the material presented in this video tutorial, you need to have ROS2 Jazzy Jalisco installed on your system. If you don't have ROS2 Jazzy Jalisco, then go to my YouTube page and search Install ROS2 Jazzy Jalisco on Ubuntu. There are several video tutorials. Follow these tutorials in order to install ROS2 Jazzy. Once you do that, let's verify that you have properly installed ROS2 Jazzy. First of all, type this command. This command will list the content of this folder. This is the standard folder for installing ROS2 Jazzy, and if this folder is non-empty, then most likely ROS2 Jazzy is properly installed. However, a true verification is to try to source or to execute this setup.bash script. So run this command, and then after that, try to print out this environment variable. If you see Jazzy, this means that ROS2 Jazzy is properly installed on your system and you can continue watching this video tutorial. The next step is to install the necessary packages. Now, every time you want to play with ROS2 or with any type of ROS2 program, you need to source the environment. We actually did it by executing this command. However, I will show you this step once again. So let's close this terminal and let's open a new terminal. And let's say we want to start in this terminal and we want to play with ROS2. The first step is to execute this command. By executing this command, we are creating the so-called underlay. So what is an underlay? Underlay represent a set of parameters and configuration that enables you to run the ROS2 build commands and that enables you to execute ROS2 programs. These parameters and configuration are defined in this setup.bash script. Sourcing a file, meaning that you are actually executing the script inside of this file. So once you do that, you can continue further. Now, every time you want to install a new program on Linux Ubuntu, you need to execute these two commands. These two commands will first update the package list on your local computer, and then all the packages will be upgraded. Here, enter your password. This is your super user password, and wait for a while. I usually run this command once every week, and my suggestion is to do that. Press Y and be patient. The next step is to install Gazebo Harmonic on our system. Note over here that there are several versions of Gazebo. And for every version of ROS2, we have the corresponding or suggested version of Gazebo. In case of ROS2 Jazzy Jalisco, the recommended version is Gazebo Harmonic. However, independently from your version, you can run the single command that will automatically detect your ROS2 version, as you can see over here, and that will install the corresponding Gazebo version. So let's run this command, and as you can see over here, Gazebo is already installed on my system. However, in your case, it might take a while to install Gazebo. Next, let's make sure that Gazebo is properly installed. And here comes the trick. You need again to source your underlay because you need to refresh the packages that were just installed. So run this again, and then first of all, let's run this command to see that Gazebo is actually installed. You can see the installation folder of Gazebo executable, and then let's try to run Gazebo by running this command. So let's see what will happen. And if you see something like this, this means that Gazebo is properly installed. So let's try to, for example, select here and click on run and see if we can run everything. And here it is. So this is a humanoid robot, probably some Japanese type of humanoid robot. And over here you can actually control the motion of robot. However, to do that, you still need to activate your controller. To activate the controller, you need to play this button, and then you can actually move ahead. You can do yaw, pitch, also for the leg, etc. Okay, so let's close the simulation and let's continue further. Next, we need to make sure that we have the necessary set of ROS2 packages that will enable us to implement the simulation. And most likely you have them. However, if you installed a non-complete ROS2 version, then most likely you don't have these packages. So let's try to install the packages. First of all, we need to install ROS2 Jazzy Joint State Publisher by running this command. Then we need to install Publisher GUI. Then we need to install a very important Zacro package that will enable us to parameterize the robot geometry. This will be explained later on. And then again, we need to install these additional Gazebo libraries. Most likely they are being installed. However, let's try to execute them. Okay, now let's verify that we have the packages on our system. The most important are Gazebo packages. To verify the package list, we will write this command. Then we are going to use grep, and then we are going to search for all the packages containing GZ. And let's see what it is. We can see Gazebo packages. Search for ROS_GZ, here it is, and ROS_GZ bridge. These are the most important packages that we will need in this video tutorial. The next step is to create a Workspace folder and to create our empty package. And again, to teach you and to remind you that you always need to source the environment, let's close this window. Let's open a new terminal window. And inside of this new terminal window, let's again create an underlay by sourcing this file, and then we can continue. Then go to the home folder. Note over here that tilde is an alias or nickname for the home folder, and inside of the home folder, let's create our base or workspace folder called WS Mobile, and inside of that folder, let's create the source folder. And then let's navigate to the source folder, and inside of this folder, which is currently empty, we need to create our empty package, or better to say, to create our template. Okay, now here's one very important thing to keep in mind. Whenever you want to create a package, you need to go to the source folder inside of your base workspace folder, and in that folder you need to execute this command. The name of the command is ROS2 package create. Then you need to specify the build type. It's going to be AMENT CMake. CMake is a build environment or a build system for compiling C++ programs. And then we need to specify the name of our package. In my case, it's mobile_robot. And after you press this command, and if you scroll up, you will see that several packages, or better to say, several folders and files are being created. If you now list the content of the folder, you will see our package folder. So let's navigate to this folder. Okay, inside of this folder, we need to create several additional files, or better to say, several additional folders. Here are the folders. and this command will create them. First of all, we need the launch folder, then we need the model folder, and then we need the parameters folder. After executing this command and after listing the content, you will see launch folder, model folder, and you will see the parameters folder. Let's thoroughly explain these folders and files. First of all, cmakelist.txt is a configuration file that tells to our build system how to build our package. We will modify this file later on. Then include folder is a folder that can contain some file that we want to include. We are not going to change the content of this folder. Then we have the launch folder. Usually the launch folder contains the Python launch files, and we will create that file later on and store it in this folder. Python launch files are files that are used to start several nodes at the same time. Then we have an additional model folder. This folder is going to contain our geometrical description of the robot as well as additional Gazebo files. Then we have another configuration file, package.xml. We will edit that file later on. Then we have the parameters folder. In this folder, we are going to store a YML file that defines how ROS2 topics should be connected to Gazebo topics. And finally, we have the source folder. Inside of this folder, we are going to store our C++ file. The next step is to create the URDF or Zacro files as well as the Gazebo and the parameter files. The URDF file defines the robot geometry and robot inertia properties. These files, that is the URDF file, there will be two files, should be placed in the model folder. So let's navigate to this folder, and here you have several options to create files. You can, for example, use the standard Linux Ubuntu editor such as Nano or some other favorite editor. However, in this video tutorial, I'm going to use Visual Studio Code. If you don't have Visual Studio Code installed on your system, then don't worry, go to my YouTube channel and search for Install Visual Studio Code on Linux Ubuntu and watch the tutorial. I'm going to start Visual Studio Code, and over here, I'm going to create a new file. The name of the file should be, first of all, robot.zacro. Make sure that you name the file correctly. So let's copy this file name, click on File, New File, and let me do it again, New File, and let me paste the name of the file, and save the file in the model folder. Click on Create File. Here, to save time, I'm going to simply copy and paste the content of the file. Here it is. Then I'm going to go here, paste. Oops, I didn't copy it correctly for some reason. Then let me do it over here, and here it is. In order to properly explain this file, I'm going to change the size of this window. And then in parallel to this window, I'm going to bring up this robot description. So here it is. Now, we can look into this file, and at the same time, we can read this document over here that properly defines the complete robot description. However, let's briefly explain this file. This is an XML file that defines the robot geometry. Consequently, you need to start the file like this. Over here, you can see the comments. Let me now expand this so you can see how the comments tags are started. They're started like this and they end like this. As always, the suggestion is to comment the file. So everything from here to here is a comment section. Then we need to start the robot description by using this tag on the code line 9. We specify robot. This is the tag. Then inside of the tag, we specify this parameter name. Here I'm naming the robot. And then this part is standard. Note over here that this tag is opened on the line 9. And if you scroll all the way down to the end of the file, you'll see that the description ends with robot. Okay. This file has 271 lines. However, many lines contain comments as well as repetitions. And I'm going to explain them thoroughly. Okay, next, we need to define the proper constant. Here, we are using the macro tag, then we are specifying the property, then we are specifying name, and here I'm calling this variable or constant pi constant, standing for pi. Later on in the text, we are going to use this variable name or parameter name whenever we want to refer to pi. And finally, I specify the pi value up to a certain precision. Next, we need to define the body dimensions, and for that purpose, we need to look inside of this graph. You can see that the robot dimension is completely being parameterized. That is, instead of specifying at every time in the code 3.14.123, I'm going to simply define variables. I'm going to call them A, B, C, and then I'm going to refer to these variables later on in the text. In this way, we completely parameterize the robot geometry, and we can easily change the parameters over here if you don't like them. To define a parameter or a variable, you need to use again macro tag, then you need to specify property, then you need to give a name, and you need to give a value, and that's it. So let's see what is A. If I bring back this document, we can see that A is this dimension. Let me zoom in a little bit so you can see it even better. So this is A, and it's equal to 1. Then you can see B. Where is B? B is the height of the body of the robot. Where is C? C is, let's find where is C? C here. You can see it over here. It's the width of the robot body. And then we need to define the wheel and caster dimensions. Namely, our robot has two wheels. Here is the first wheel, here's the second wheel, and it has a caster wheel. A caster wheel is non-active or passive wheel that provides robot support. We are going to control wheel 1 and wheel 2. And let's define the dimensions. You can see the radius of the wheel. Here is the radius of the wheel. And then you can see wheel width. Here's the wheel width. Next, we need to define these geometrical values S1, S2, S3, and S4. So let's see S1. Here it is. You can see how S1 is defined. Namely, here we are referring to the previously defined variables. And we are saying that S1 is B over 2 plus R. So where is S1? Let's find it on this graph. Here is S1. S1 is displacement of the center of the body of the robot with respect to the ground plane. Here it is. What is S2? Let's find S2. S1, we can see S2, let's try, yes, S2 is here. This is the distance, horizontal distance between this point and this point. Point C5 is the center of the wheel. That is, in this way we can place the wheel by varying S2. Then we need to define S3. So where is S3? Let's see. This is S1, S2, and S3. S3 is the distance, horizontal distance between C2 and C3 point, and C3 point is the center of the caster. And then we have S4. We can see that S4 is displacement in this plane from point C5, which is the center of our wheel, with respect to this point over here. Simple as that. And in this way, we have defined geometry. Next, we need to define the robot mass and inertia properties. Okay, so let's start with material density. Here you need to define the material density. In my case, this is a density of aluminum. Then we need to define the wheel material density. I will call it as D2, and here is the value again, aluminum. And then we can see the caster material density. Here it is, it's again aluminum. Then we need to define the robot mass, wheel mass, and the caster mass. For that purpose, we need to use the formula mass is equal to density times volume. Okay. Some of you are not familiar with volume of basic geometry basic geometrical shapes, and for that purpose you can look over here. So first of all, what is the volume of our robot body? Robot body is a simple box, and its volume is A multiplying B multiplying C, height, width, length, right? And then the mass is simply D1 multiplying ABC, and that's precisely what is written over here. How about the wheel? Wheel is a cylinder, and here is the mass of a cylinder, and here are the geometrical properties. First of all, the volume of a cylinder with a height of D and the radius R is given over here, and here you can see the Zacro implementation. And let's then talk about the caster. Here's how the caster mass is implemented. It's basically a sphere. So what is the volume of a sphere? Here is the volume of the sphere, and you can see how this thing is being implemented here. And mass is simply a density multiplying the volume, so we have defined over here mass of our caster. Next, we need to define moments of inertia of the robot body. Again, we are using parameters. So let's start with the robot body. In our case, the robot body, let me actually move this like this so you can see it. Maybe like this, it's better. Okay, it's much better right now. So what is a robot body? Well, a robot body is a box. Okay, and we need to define the moments of inertia of the corresponding axes. We have Ix, Iy, and Iz. Our coordinate system is placed in the center of our body, and the products of moments of inertia are equal to 0. Consequently, we just need to define Ix, Iy, and Iz. And here is the formula for Ix. Here's the implementation. Then you can see the formula for Iy, this line. And over here you can see the formula. And finally, you can see the formula for Iz, and you can see implementation. Good. How about the wheel? Well, if you go now and we look at the wheel, here is the Ix for the wheel. And here's Iy for the wheel. And here's Iz for the wheel. Here we will have only definition of Iz and I wheel, which you can see the implementation over here because Ix is given over here. Okay, let's continue further. Next, we need the moments of inertia for the caster sphere. And here's the formula. And over here is the implementation. Note over here that since everything is symmetric, we have only a single formula, and this is also the case for basically moments of inertia of the wheel. So we only have actually two formulas. We have a formula for the Ix and the formula for the Iz, and that's it, since Ix and Iy are the same. Okay, let's continue further. Next, we need to define the complete inertial section of the robot body. We're going to use this inertial section later on in the code, and here's how we define it. We start the macro name, inertia body, we define the inertial section, then we define the origin of the body. For that purpose, you need to look into the inside of this document to know how the origin is being displaced. If I now go back over here, you can see the displacement is actually S1. Then we define the mass value over here, and then we define the inertial section, Ix, Iy, and Izz, and that's it. Later on in the code, we are just going to type this inertia, or we are just going to type inertia body, and we are not going to paste everything over here since it will be automatically parsed. We do the same for the inertial section of the wheel. Let's bring up the formulas and the graphs, and let's see what's happening over here. First of all, we need to define the inertial section, we define the origin, we define the mass value, and we define the inertial section over here. Note over here that we have basically rotation, since the coordinate systems of the wheels are being rotated. Then we have the macro that defines the complete inertial section of the caster. The principle is the same. Let's just bring the formulas over here. We have the inertial section, we have the origin, we have the mass, and here's how inertia is being defined. And that's it. Next, we need to include additional files. Here, we need to include a file that will define a differential drive plugin for controlling our robot, and we need to include the file, or basically better to say all the parameters are in the same file, and these additional parameters contain additional Gazebo values and parameters. To do that, we simply type this line. However, over here we still didn't create this file. We are going to create this file later on. Its name is going to be robot.gazebo. Okay, let's continue further. Next, we need to define links and joints. First of all, we need to start with the fictitious link of the robot. Its name will be base footprint. Then we need to specify the joint name. Here the joint name is body link joint, and type is fixed. We need this fictitious link in order to avoid errors in Gazebo simulation. And next we need to specify the parent link, and then we need to specify the child link. So here I'm going to bring this document here, and I'm going to do this so you can see what's happening. Namely, as mentioned previously, we need an artificial link. And this artificial link is just used for Gazebo simulation, that is to avoid errors. Its parent link is base footprint, and its child link is body link. So what is body link? Well, body link is this box over here. This is the body of our robot. And let's continue further. Next, we need to define the body link of our robot. We start the link tag, we give it a name, we define the visual description. It's a box with the dimensions A, B, and C, as you can see in the graph. Then we need to define the displacement and orientation of the geometric center of the link with respect to the link frame origin. We can see that the center, that is the point C2, is displaced from the base, or basically from the base plane, and displacement is S1, and consequently over here we place S1. Since we want to simulate the dynamics in Gazebo, we need to have the collision section. Inside of this collision section we need to define the geometry of collision. It's simply equal to the geometry of our object, that is, it's equal to the box with the same dimensions, and here the origin is displaced in the same way. And finally we add this macro called inertia body, and if you go up, the inertia body is defined over here. That is, we are just using this section to add our inertia body here. Good. Let's continue. Next, we need to define the back right wheel of the robot and the joint. We call it as wheel wind joint. Here is the wheel wind joint. The wheel wind joint will actually connect the body link and wheel wind link. It's placed over here, and we need to define its dimensions. First of all, we need to specify the parent link. The parent link is the body link. The child link is the wheel link 1. And now we need to define its origin. Its origin is displaced. Here is the displacement, minus S2. So you can look at the graph. Minus S2, right? Then minus S4 here. And then you have R. And that's it. Then we need to specify the axis of rotation. The axis of rotation will be the y-axis. Then we need to specify the max torque that will be applied to this joint, and then we need to specify the max velocity. Then here we need to specify dynamics, damping, and friction. These are additional parameters defining damping and friction, which are necessary for simulating our model. Then we continue with the wheel 1 link. We need to define its visual representation. First of all, we need to define the rotation of the coordinate system. Then we need to define the geometry. We can see the geometry is a cylinder with a length of d and the radius of r. However, this link is rotated, that is, the cylinder is rotated such that it's placed like this. This is why you can see the rotational angle rho of pi over 2. This is very important to keep in mind. Then we define the collision section, which is basically just a copy of the visual section, and over here we're specifying the inertia of our wheel by just specifying this macro. And if you go back in the code, you'll see the inertia wheel, and that's the power of parameterizing everything. Let's continue further. Now, in the same way, we define the back left wheel of the robot and the joint. So let's bring up the description over here. We need to specify the joint. The joint is placed over here. Its parent link is the body link. Its child link is the wheel 2 link. Let's see how the origin is being displaced. So let's see. Minus S2, good. S4, here it is. And then we can see R, and that's it. Simple as that. Then we need to specify the axis of rotation, then we need to specify the limit effort, and then we need to specify the velocity. Finally, we define dynamics, damping, and friction. And the link, wheel 2 link, is defined in the same way as the wheel 1 link. We need to specify the origin, we need to specify the geometry, which again is a cylinder, and then we need to specify the collision properties. And that's it. Finally, we need to define the caster wheel. Here is the caster, or better to say the joint corresponding to the caster wheel. I'm calling it as caster joint. Here the type is fixed, which means that it cannot rotate. Its parent link is the body link, its child link is the caster link, its origin is displaced. Let's see, the displacement is, let's see, S3, 0 and R. Good. And we define the joint. And then finally we define the caster link, we define the origin, we define the geometry, we specify the sphere radius, the end geometry and visual. The collision is simply the copy of visual, and over here we specify the inertia property. This is a macro defined at the top of this link. So let's see, let's go up, and here you can see how it's being defined. Now if you go all the way down, you end the file, and that's it. The next step is to define an additional file containing additional Gazebo parameters. Namely, as you can see over here, we're including an additional file inside of this file. However, this file is still not being created. So let's create this file by clicking File, New File, and let's call the file as robot.gazebo. And let's save this file. Let's save it in this folder, make sure the name is okay, and over here I'm going to paste the content of this file. This file defines additional parameters that are necessary to simulate the model in Gazebo. Again, we start with the XML tag, we open the file with robot, and we close the file with robot. These are the tags that define that everything inside defines the robot geometry. And then we need to define, first of all, the friction parameters, that is the mu1, mu2 parameters, and material color for our body. We start Gazebo reference, we reference to the body link, then we define mu1 and mu2, and then we specify material. We do the same thing for wheel 1 link. Here we are using yellow color. For the body we use red. Then we do the same for the wheel to link. This is exactly the copy of this one except for the name change. And here is the caster link. And here we are specifying the color to be blue. Next, we need to use the controller, or better to say, to define a plugin that will enable us to control our robot. For that purpose, we are going to use the standard Gazebo Sim differential drive system. We specify the Gazebo tag, meaning that this is a Gazebo plugin. We end at the end Gazebo. And then we are specifying the name. We specifying the name of the class. Then we specify additional parameters. We need to define what are the wheels or the joints. We have the right joint, we have the left joint. The right joint will be wheel 1 joint, the left joint will be wheel 2 joint. Then we need to specify the kinematics. This is basically wheel separation. If you now open up the document, you can see that the separation is S4. Right, and it's basically 2 times S4, and then we need to specify the wheel diameter. The wheel diameter is 2 times R1. Then we need to specify the limits, and here comes a very important part. We need to specify the topic name. The command velocity topic will be used to control the simulation. Then here's the TF topic for the coordinate transforms. Here's the odometry topic for tracking the robot motion, and then we need to specify the child frame ID, and then we need to specify the publisher frequency for the odometry, and then we end the plugin, and then over here we need the joint state publisher such that we can publish the joint states. We are using this Gazebo plugin. Here's the name. We specify the name of the topic and the joint names, and that's it. Simple as that. Let's save this file and let's continue further. Next, we need to define an additional file that will define a bridge between ROS2 and Gazebo. Namely, we would like to use a C++ ROS2 code to control our robot. For that purpose, we need to bridge or connect ROS2 topics or ROS2 channels for communication of messages with Gazebo channels or Gazebo topics for communication of messages. For that purpose, we need to create a file called bridge_parameters.yml. And this file should be placed in the parameters folder. So let's create a file. Here I'm going to use the name. And here it's very important to save this file in the parameters folder. Click on Create File. Next, to save time, I'm going to simply copy the content of the file, and I'm going to explain the file line by line. As mentioned previously, this file bridges ROS2 and Gazebo topics. So first of all, we have the ROS2 topic name clock. Equivalent topic in Gazebo world is clock. ROS type name is the type of the message being transferred. This is the message type. Gazebo type name is given over here. Look how the names are equivalent, and direction is from Gazebo to ROS. Good. Then we need to do the same thing for joint state. We have the ROS2 topic name. This is a very standard and very familiar joint state topic. This is the Gazebo topic name. This is the type name in ROS world. This is the type name in Gazebo world. And here is the direction from Gazebo to ROS2. And here is the equivalent thing for the odometry topic. Odometry, the name in Gazebo, in ROS2 world is odom, in Gazebo world is odom also. Here is the data type in the ROS2 world, here is the data type in Gazebo world, and here is the direction from Gazebo to ROS. Then also we have for the TF topic for differential drive plugin. You can see that everything is equivalently defined, and here comes the most important topic. This is our command velocity topic that will be used to control the simulation. The name is cmd_val in both worlds. Here is the type of the message. It's the twist message, and over here you can see the Gazebo type of message, and direction is from ROS2 Jazzy. That's it. So let's save this file and let's continue further. The next step is to write the Python launch file. Let's learn how to do that. The launch file name is given over here. So let me copy this name. Then let me go to Visual Studio Code, click on File, New File, specify the file name. Oops, let me do it again. Here I'm going to specify the file name and make sure that you save this file in the launch folder. Let's create this file. Then, to save time, I'm simply going to copy and paste the content of this file. Here it is. And let's explain this file line by line. First of all, let's look at the global picture. The purpose of this file is to start several nodes at the same time. You will see the nodes that we will need to start later on. First of all, I need to import the necessary libraries, packages and modules. Then I need to define a function which defines how everything should be executed. First of all, I need to specify the robot Zacro name. This name has to match the robot name in a Zacro file. If I open Zacro file and if I go all the way up, here's the name of this robot. Good. Then I need to define the name of the package. It's called mobile robot. This is the name we use to create our package. Then I need to specify a relative path of my robot.zacro file with respect to the path of my package. The path of the package is actually this path over here. And my model is actually stored in the model folder, and the name of the file is robot.zacro, and that's precisely what is written over here. Next, I need to get the absolute path to the model. For that purpose, I'm using ROS2 path joint. Here, this command will get the base package path, that is this, it will retrieve or return this path, and then I'm simply adding this relative path of my model. Then I'm getting the robot description from the Zacro model file. For that purpose, I'm using this command. And then I need to call the function Python launch description source. Then I need to specify the path. Note over here that this line is going to return the absolute path of my Gazebo simulation. This is basically the standard package of Gazebo. Then I need launch, and then I need this executable. That is, I need to get the file from the Gazebo ROS2 package, the launch file, and here it is. And here's the absolute path to that file. This is the name of the file, and this is how we retrieve that path. Now, since we're using an empty world model, we need this line. You can see it over here. Let me move this. Here you're specifying arguments. Here's the name of the file, empty.sdf, and then here are some additional parameters that we need to use. Then we need to define the nodes. First of all, here's our Gazebo node. We need to specify the name of the package, name of executable, arguments, and the output. Then we need the robot state publisher. This is the standard ROS2 node inside of the robot state publisher. Here is the executable, output is the screen, and here we are passing the robot description that we read previously, and we are using the simulation time. Next, we need to define the bridge. First of all, we need the bridge parameters. Here we need to retrieve the path of our bridge underscore parameters.yml file. That is this file over here. We need to get the absolute path of our package, then we need to get the parameters folder, and inside of that we have our file. And then over here we are actually defining the ROS2 Gazebo bridge node. the package is here, executable is here, and then here we are passing our file bridge underscore parameters YML. Then we are creating an empty launch description object, here it is, and we are adding the corresponding parameters and corresponding nodes, and then we are simply returning the launch description object, and that's it. So to summarize, this file will start this node that will bridge ROS2 and Gazebo nodes or topics. Then we are starting this robot state publisher, and we are also starting the ROS Gazebo simulation node. Simple as that. Let's save this file and let's continue. The next step is to implement the C++ file for controlling the robot motion. To do that, click on File, New File, and call the file as test.cpp. And let's store this file inside of the source folder. Click here, go to Source, and Save File. Here, to save time, I'm going to simply copy and paste the content of my C++ file. On my YouTube channel, there is a separate video tutorial thoroughly explaining how to write C++ files for controlling ROS2 programs. Here, I'm going to briefly go over this file. First of all, whenever you want to use C++ inside of the ROS2 environment, you need to include the RCL-CPP. RCL-CPP is the ROS2 client library for C++ that is included with any standard installation of ROS2. This library provides the standard application programming interface or API for controlling ROS2. Then we need to include geometry messages of the type twist. For that purpose, we need to include this header file. So what is a twist message? A twist message is the message containing command velocities for our robot. In our case, since the robot lives in a two-dimensional space, we are going to send only linear velocity in the local x-axis direction or the body x-axis direction, and the angular velocity around the center of the robot. This is very important. Then we need to include input-output stream since we want to print some messages, or optionally you would like to print some messages. Everything is embedded inside of the main function. First of all, before using the RCL-CPP, we need to initialize it by using the init function. This is what is written on the code line 39. Then we need to define the message that we want to send. The message is of the type geometry message, message twist, and I'm going to call it as control velocity. Then over here we need to specify the components of the linear velocity vector. Namely, our twist message, whose name is control velocity, contains two sub-data structures. We have linear and angular. Linear defines the linear angular velocity, and here I'm only specifying the x-axis linear velocity. Namely, if I bring up my model, you can think of x-axis linear velocity as the velocity that's always in this direction. However, robot rotates. That is, the x-axis rotates together with the robot, and the velocity is always in this direction. That is, we're moving forward. Y is 0 and z is 0. And then over here I'm specifying the angular velocity only around the z-axis. Z-axis over here is centered here and pointing toward us. That is, I'm also giving linear, or better say angular velocity, such that the robot also spins. These two combinations, that is the combination of x is equal to 4 and z equals to 8, will produce a circular motion of the robot that you have seen at the beginning of this video tutorial. Next, I need to create a node. For that purpose, I'm writing this line. And then, in order to publish the messages, I need to create a publisher. Here's how I do it. And then over here I need to specify the rate. The rate tells us how often we are going to send messages. In this case, I'm sending messages every 1000 milliseconds. That is, I'm going to send messages every 1 second. And here's the main while loop that we use to control the robot. We are simply calling publisher, publish. What we are publish control velocity. And here's how the control velocity is defined. Then we are spinning the node, that is we are starting everything, and code will stop over here. That is, this command will make sure that the node is continuously running and that our simulation is continuously running. After you press, or actually I have to correct myself, this is not the blocking statement. This statement will be executed only once. So correction, this statement will be executed only once. And over here we are actually enforcing that the frequency of control is being respected by sleeping for 1000 milliseconds. That is, by ensuring that the corresponding rate defined over here is being enforced. And then finally, if a user presses Ctrl C, this will break, we need to shut down, and we need to return 0. So let's save this and let's continue further. The next step is to modify the package.xml and the cmakelist file. These are the configuration files. Let's open them. First of all, click on File, New File, then go to the base package folder and open package.xml. Here it is. Then over here, after line test dependencies, you need to add these lines. Let me copy them and paste, and let's explain the purpose of these lines. First of all, these lines are telling to our build system that our package depends on the standard or the previously installed ROS2 packages. That is, it depends on Joint State Publisher, Robot State Publisher, ROS Gazebo, ROS Gazebo Simulation, ROS Gazebo Bridge, Zacro, RCL CPP, and geometry messages. So let's save this file and let's continue further. Next, let's open a cmakelist file, and over here, after this line, find package, we need to add several lines. Here you need to be very careful because the order really matters. Let's start with these two lines. First of all, these lines are telling that our C++ file, that is our source file, depends on RCL CPP and geometry messages. Namely, if I open my test.cpp, you can see that I'm including RCL CPP and geometry messages. Good. Next, I need to create an executable for my test.cpp file. Not a big deal. To do that, I simply need to add these two lines. First of all, here I'm defining the executable. It's called test_program, and here I'm specifying the source file for this executable. Namely, my test.cpp file is located under, or better to say, in the source folder. Then I need to specify that my executable depends on RCL CPP and geometry messages header files. That is, to build, I need to also include some additional header files. Good. Let's continue further. Next, we need to install these executables, and we do it like this. We are installing targets, test program, that's the name of executable, and here's the destination. Simple as that. Let's save this and let's continue further. And finally, we need to add these lines. That is, we need to tell to our build system that during the process, that actually after creating the package, we have created the launch, model, and parameters folders, and our build system need to know that there are some files located in these folders. So let's save this file, let's save package.xml, let's save test.cpp as well as all the other files, and let's proceed further. The final step is to build everything and to run our programs. For that purpose, remember to always go back to the base workspace folder. That is to go over here. Inside of this base workspace folder, we will run the colcon build command. However, before we run this command, we have to make sure that all the packages are properly being installed. That is, that all the dependencies are being installed before we build. For that purpose, we are going to use ROS2. Consequently, install ROS2 by running this command. Then let's initialize ROS2. And then finally, let's update ROS2. And finally, we need to run this command. And if you see something like this is very good and promising, and you can proceed further with building the package. To build the package, you simply need to run build command, and hopefully we will not see any error. Let's see. No errors, no warnings. This is a very good sign. So now let's run the created nodes and let's inspect the execution. To do that, you need to open a new terminal. And in this new terminal, we are going to run the Python launch file. To do that, you need to source the overlay. Note over here that we are now executing setup.bash file inside of the Workspace folder of the created package. That is, we are not installing, or better to say executing, setup.bash from the base ROS2 folder. So execute this, and then we can run our launch file. To do that, simply run this file, or type ROS2 launch, then the name of the package and the name of launch file executable. And let's hope that everything is fine. And voila, here it is. Beautiful, beautiful. Here's our robot. Currently the robot is moving since we are not sending any command. Okay, next we need to run our C++ code. To do that, open a new terminal, and inside of this new terminal we need to do several things. Again, we need to source the overlay, that is setup.bash file, from the created workspace, and then we need to run our program by running this command. We use ROS2 run, then the name of the package, which is mobile robot, and the name of the executable defined in the CMake file. And if I run this, bang, and if I open my folder, or actually my Gazebo simulation, you will see that my robot is moving. And this is what we expected. Now, if you want to inspect what's happening behind the scenes, you can open a new terminal, and inside of this new terminal, you can first of all source the underlay by running this command. Then you can type ROS2 topic list to see what are the topics that we currently have. Here they are. For us, the most important topic is command velocity. Then you can type something like this, ROS2 topic, for example, echo, and then you can type command velocity, and this command will tell you what is being currently sent through our command velocity topic. And as you can see over here, we are sending the angular and linear velocities, which are precisely defined in our C++ code. Also, you can echo the odometry topic. So if you now type again list, the odometry topic will track basically the position and angle of rotation of the center of the robot. So we can simply again type something like this, odometry, and then you can see in real time how the odometry is being transferred. You can see the twist messages, which are position and orientation, and as well as other things. Okay, that's all for today, and thanks for watching.